Welcome back to the GCSE Maths Pro YouTube channel. In today's video, we'll be looking at some of the hardest Edexcel past paper questions. So straight in at this one, it is only 2 marks, but I feel like it's hard because in my head it's more similar to A-level stuff. So it's more so one of those ones where once you know what to do, it's actually not so hard, but I feel like a lot of people don't necessarily know how to tackle this one. So we've been given the graph of y equals sine x, as you can see, just between 0 and 360. So using this graph, find estimates for all 4 solutions of sine x is equal to 0.6. And then also just note this, they have said between 0 and 720. So that's double the graph that we can see. So you might have seen something similar to this before, but not with trig graphs. Originally, let's have a look at the equation. It's y on one side and sine x on the other. Now look down here. I know it's swapped, but that's still sine x. That means that the other side is still y. So that tells me that I'm looking for where y is 0.6. So get my ruler and just draw a line at 0.6 as best you can. This is obviously just 1 square above the halfway point. I am continuing it because I'm going to try and fill in the rest of that graph as well because it is double, isn't it? But you've got 2 options for your first answer. You can either just look here where it crosses. You can see it crosses in 2 places originally, just of 0 to 360. What you can do is just try and read this bit off if you want. So there. Or, I know it's an estimate, if you want a slightly more kind of accurate idea of what that would be, you can use your calculator as well. But this does only work for the first value. So what you can do is obviously sine inverse of 0.6. Now, that's the exact value. Obviously, I guess there's more decimals. But because they want an estimate, what you could do is just round that to, say, 37. And say, right, the first one is obviously about 37 as an estimate, isn't it? So this is 37, so that's one of your solutions. Even if you just get 1, that's already one of them. X is 37. Now let's deal with the second one that we can actually see. Now the sine and cosine graphs, both of them, are symmetrical around certain points, aren't they? Do you see how it's symmetrical around the point 90? 0 to 180, there's a line of symmetry here, isn't there? Also down here, there's a line of symmetry at 270 between 180 and 360. So what that means is if this distance here from 0 to that point is 37, then symmetrically backwards, this distance is also 37. However, we're obviously going backwards from 180, aren't we? So to work out that second solution, you would just do 180 minus the 37, which you can see is 143. So you can get those first 2 solutions like that. Now, the other 2 solutions are obviously somewhere over here. So there's my rough continuation of the graph. Obviously, this one is then the 720, isn't it? And then hopefully you can figure out that this one here is 540 because it's another 180 from the 360. Do you see now we've got 2 other places where it does cross? We can't necessarily read them off using the scale anymore, but I'm going to do the same thing with symmetry. It is still using 37, but we're just starting at a different point. Instead of starting from 0 here to get 37, we're starting from 360 again and doing another 37. So do you see how that one would obviously be 360 plus 37, which is obviously 397. So that's your third solution, 397. And then this one here, the one around the 540, is the same logic as the one around 180. We're going backwards using that symmetry from 540. And again, it should be another 37. That width will always be the same. So you just do 540 minus 37 again, which obviously gives you 503. There's your answer. We've got here a regular hexagon with side lengths x. So the A, B, C, D, E, F is the smaller one. So each of these side lengths for the smaller one, the white hexagon, are side length x. This hexagon is then enlarged center F. So you can see the corner F, they've just enlarged it away from that corner by the scale factor P to give hexagon F, G, H, I, J, K. So the bigger one, the grey one. Show that the area of the shaded region in the diagram is given by 3 root 3 over 2 brackets p squared minus 1 x squared. We're not going to work out what x is, we're not going to work out what p is, that would be impossible, right? We don't have enough information. We're just trying to create this kind of expression at the end and show that we can simplify it and format it to look like this. So first of all, how do we work out the area of a hexagon? There's not necessarily a formula that we all know, is there? So that's why I would try and split it up. Now, it's a regular hexagon, that's key information. Do you see I can draw a triangle there and a triangle here and then technically a cross as well. So I've got 6 identical triangles. Now, because this is a regular hexagon, all of the sides are the same, we can split it into these 6 equilateral triangles. Equilateral triangles where all the sides are the same, aren't they? So like in here that would be x, that'd be x. On the outside it's x. You get the point. They're all x as a side length. How do we work out the area of an equilateral triangle? Well, this is where I would lean towards using the area of a triangle, the trigonometric version. So the area of a triangle using the trig version, which is on your formula sheet, is half AB sine C. Now you're thinking, well, what's the angle? Well, if it's equilateral, it has to be 60, doesn't it? 60 degrees. And then AB are the two sides surrounding it. So that's half x times x, which is x squared, sine 60, which if you put in your calculator gives you root 3 over 2. And then if you multiply that by a half, that would be root 3 over 4 x squared. I'm putting that at the front because that's the coefficient, isn't it, the number? So we need to know the area of the smaller hexagon first. That one, as we said, times by 6. We want to have 6 of those together, don't we? So 3 root 3 over 2 x squared. That's the area of the smaller one. Now we want to know the area of the bigger one. This is where our scale factor p comes in, if you remember that bit. I'm going to do exactly the same thing. However, what are the side lengths of the bigger hexagon? So for example, if we look at HI, that would be xp. It would be the size of x multiplied by the scale factor. This one would be xp. All of them are xp. And if we get our triangle again, we use a different colour this time, just roughly where the centre is. That's xp, that's xp. We know that this is still 60 because it's still an equilateral triangle, just a bigger one, isn't it? So the area of that is still half AB sine C, but our AB, which are the two sides, have changed. It's now xp times xp sine 60. And then I just simplify that. So half xp times xp is x squared p squared. So you can see we're starting to get p squared in here as well. Sine 60 we know is root 3 over 2, isn't it? Again, we want 6 of those, don't we? So then that would become the same fraction, basically, just with an extra p squared at the end. 3 root 3 over 2, x squared, p squared. That's the large one, the big one. So if we want to know the shaded area, the last thing we want to do is subtract the 2. So the big one minus the small one, that's the area of the shaded region. But do you see how they've written it differently? So now that we've got the area, we just need to format it differently. They've effectively factorised it by pulling out this and this, just for some reason they put one on the left and one on the right, haven't they? So they pulled out 3 root 3 over 2. I'm going to put the x squared here for now. What would you get left with? Well, the first one you can see is p squared. Now this one doesn't just disappear, right? It's not 0, it's minus 1. We've got that. Obviously they've just put the x squared at the end, so you can write that. And that's it. So here is the frustum of a cone. The diagram shows that the frustum is made by removing a cone with height 3.2 centimeters from a solid cone with height 6.4 centimeters and base diameter 7.2. They love to give you the diameter. Obviously, all of these formulas are in terms of radiuses, so just be really careful. They do often give you the diameter, not the radius. The frustum is joined to a solid hemisphere, again of diameter 7.2 centimeters, to form the solid S shown below. So not only is it that they've given you the diameter, they've also given us, for Edexcel, they'll give you always the volume of a whole sphere, but here we have a hemisphere, so you also have to remember to work with dividing that by 2 as well. Then they've said the density of the frustum is 2.4 grams per centimetre cubed, and the density of the hemisphere is 4.8 grams per centimetre cubed. Calculate the average density of the solid. So you do also need to know a formula for density as well. This is not given to you. Density is mass over volume. I like to use it in the formula triangle just in case I need to rearrange it. In this case, we're just looking for density. So I need to know the total mass of the shape and the total volume of the shape. So probably the easiest place to start is with the volume, isn't it? They've given us those formulas. So we could do it in order. They've said the volume of the sphere first. Let's do that. The volume of, in this case, we want the hemisphere, isn't it, though? I'll put H for hemisphere just so you don't forget what all of these are, is 4 over 3 pi, and then the radius cubed. So remember again, radius, half of 7.2 is 3.6, and then that's cubed. But again, half of the whole thing because it's not a whole sphere. So unfortunately, we do get a really long number there. So 97.72 maybe for the volume of the hemisphere. I might decide to store this. So I'm going to do shift store and then to my letter, let's just use A, so I can bring that back later. Now we want the volume of the frustum. So obviously to find the volume of a frustum, you have to find the volume of the big cone and then subtract, or just kind of chop off the volume of the top cone, the small cone. So it's a few different steps that. Volume of, I'm going to say big cone, again so we don't get mixed up. So we've got the big cone is just a third pi, again radius, which is the 3.6, not the 7.2, squared this time, and then times by the height, which we know is 6.4 for the big cone. So that one we can work out straight away. Again, unfortunately, it gives us kind of an annoying number, 86.858-ish. Now, to work out the volume of the small cone is obviously the same formula. However, we do have the height of the small cone. The thing we are missing is the radius. We can't use the same radius because it's not, is it? We need to know the small radius. So this is the thing I think that makes this question, I guess, tricky, is just knowing this information or not, really. Because if you imagine the small cone, they both start at the same point, and then if you were to kind of drag it and make it bigger, they're the same cone. What I mean by that is they are similar cones, aren't they? They're similar shapes. One is just a much bigger scale of the other. So I just need to scale back down the radius. So figuring out the scale, what I would do is use the heights because I have both measurements. I know the small cone is 3.2 and I know the big cone is 6.4. So the scale factor, you can divide it however you want, but I like to always, I just like to divide the big one by the small one. You can see, you might be able to see what this is. That's obviously 2. So what we're saying is the big cone is twice as big as the small cone. So the radius for the big cone is twice as big as the radius for the small cone. So volume of small cone, the radius of the small cone is just half of the radius of the big cone. So just be careful because we've halved the diameter to get the radius, but then we're halving the radius again to get the small radius. So it's a little bit complicated. So we've got a third pi, and then the radius is now 1.8 squared, and then the height is the 3.2. So just make sure you're subbing in the right numbers. Is 10.86, let's say. So the frustrum is obviously just subtracting those two. So that answer's still there, isn't it? I did save the previous one as B, so I can just take that away. I guess you could probably work it out by subtracting it straight away, but there we are. So we get about 76. So 76 is the volume of the frustrum. So the volume of the whole shape is obviously the hemisphere. Don't forget that was the 97.72 plus the 76. Now I did save that under A. So I've got my 76 plus alpha A, and that gives me 173.71. So now I've got the volume of S. I also need to then know the mass of S. So to find the mass, I just need to do density times the volume. So I've got the individual volumes, I've got the individual densities in the question. So the mass of the frustrum would be 2.4 multiplied by the 76, which I did save under C, so that's the whole thing with all the decimals. So let's say 182.4. And the mass of the hemisphere, same thing, 4.8 times 97.72-ish, which I also have saved under A. So that's 469. So the total mass is obviously just adding them together. So just take my answer. That's 182.4, 651.4-ish. So finally, the density would be the total mass, which was 651.4, over the total volume, which we had is 173.71. And that should give you 3.7499. Now, they haven't said how to round it, so I feel like for me, I'd probably round that to 3.75 because it just seems like a nice way to round it. But I don't think they would mind too much as long as you do give at least one decimal. So the diagram shows 3 identical circles inside a rectangle. Each circle touches the other 2 circles and the sides of the rectangle as shown. They've said the radius for each circle is 24 millimeters. Work out the area of the rectangle. So thinking about it, area of a rectangle would be length times width. So we need to figure out the length and the width. Now, initially, the first one is quite easy because of the top 2 triangles, you can see, we draw some lines across there. We know the radius, don't we? So we know that that's 24. The other side of it's also 24, another 24, and another 24. So you see how that goes the whole way across. So I know that that would be 4 lots of 24 would be the width of our rectangle. So that's the first thing you can do immediately. So this is 96 millimeters. Now, if you look vertically, it's not the same, is it? I know that's 24, I know that's 24, but then do you see how this overlaps a bit? There's like an overlap and we don't know by how much. So it's obviously not as simple as just doing 4 lots of the radius again, and obviously that would make a square, which they've told us it's a rectangle. Where can I create other shapes? In this one, do you see where the center of each circle is? I could create a triangle there. In fact, we know that that's an equilateral triangle because, again, from the center of the circle to the circumference is the radius, 24. Same here, another radius, another radius, another radius, and so on. You get the point. So we know it's an equilateral triangle. What do we know about equilateral triangles? Obviously, apart from all the sides are the same, all the angles are the same. So we know that this would be 60 degrees, 180 divided by 3 is 60. And then we know the side lengths would be 2 lots of 24. Now, what do we actually want to know? We don't really want area in this case. What we do want to know is the length of our rectangle. So if I get my line back, you see how that would be a radius? And then this would be a radius. So what I want to know is the height of that triangle in the middle. Splitting an equilateral triangle in half makes it a right angle triangle, or two right angle triangles, right? There's a right angle, there's a right angle. You've got two options here. Because we know it's 60 degrees, equilateral triangle, you could use trig, SOHCAHTOA, or you could just use Pythagoras because we know that the base of the triangle is 24 and then the hypotenuse is 2 lots of 24. That's completely up to you, whichever you prefer. So let's just look at this green triangle here. We can recreate that. So we want to find the opposite, and we've got the adjacent. We can therefore use tan, TOA. Because we're looking for the opposite, cross that out. So my actual calculation is going to be tan of the angle times by the adjacent. Now, you could write down all the decimals. For now, because it's not our final answer, I'm going to write it down in the most simplified form, which is 24√3 millimeters. So that's our height here, isn't it? So the last thing then is if I want to work out the length of my rectangle. Remember how I said we know that this height here is a radius. This is a radius, so that's 2 times 24 plus our answer here. So we know the width was 4 times 24, which was the 96 that we already have. And we know that the length of the rectangle is 2 times 24 plus the 24√3. Which, just for now, because again, not final answer, I'm going to write it as 48 plus 24√3 millimeters. So, now back to the original point of the question. We wanted to know the area of the rectangle. That's the easiest bit, isn't it? Area is length times width. So we've got 48 plus 24√3 times by 96, which now we will put in our calculator. And they've said correct to 3 significant figures, so now we can actually write down our answer and round it. 3 significant figures would be 8,600. And that's millimeters squared. There's your answer. Here we've got ABC as a triangle. D is the point on BC such that the angle BAD and the angle DAC are both x. We need to prove that AB over BD is the same as AC over DC, so talking about sides now. So we do need to set up some form of equations that we can then have the sides involved in. Now we've got scalene triangles here obviously, so I'm thinking either sine rule, cosine rule, or maybe even the area of a triangle. Any of those would relate to these types of triangles with angles, with sides, and would form equations. I might do the area. Let's do that. So on your formula sheet you've got the area is a half AB sine C. That's obviously based in terms of the angle being C, so we do need to be a bit careful in this case because they have put the angle as A. So you'd have to figure out that you do sub in the values correctly because we do want to keep the labels in this case to match what they've given in the answer. So for the first triangle ABD, so area of triangle ABD would be half, and then it'd be the two sides when it's AB multiplied by AD, and then multiplied by sine of the angle X. So you see how I've included AB and AD. Now, because I don't actually know the area, and the area doesn't really link to the second triangle at all, does it? What I might do is on this side, write the area in a different format. So you know we've obviously used our trig version. You could also use half base times height or base times height over 2. Now, I know we don't know the height of the triangle because it has to be the perpendicular height, doesn't it? It'd be that. But that would technically be the same for both triangles, wouldn't it? They both have the same height, so it doesn't really matter that we don't know what it is. We could just use the letter H to represent that. Now, we've also then got the base BD and DC, which is also what is in this final equation, so that's helpful too. So I would normally put a half base, so the base of this first one's obviously BD, and then multiplied by the height. Those are equal because they're both different ways of finding out the same area if you obviously knew what the height was. So I'm going to do that for the second triangle as well. This one is a half, the base is now DC, but the height is still the same really, isn't it? So that's H again, and then half times AD times AC, and then still sine X because it's the same angle. So I've got two equations, but I now need to link them because obviously I only want one answer, one equation. So for this particular case, what I think I might do is just divide the two equations, because I can't show that the two areas are the same, because they're not, you can see that. But I could just, if you think about simultaneous equations, I could just divide them, couldn't I? You can technically do whatever you want, add them, subtract, divide, multiply, but I'm going to divide them in this case. So draw a massive divide line. Do you see how obviously half of it's going to cancel out? Halves will cancel out, halves will cancel out. The h's would cancel, which is why I didn't really care that I didn't know what the h was. The ads would cancel, and then obviously the sine x's would cancel. What am I left with? You can kind of not really see, but I'm left with BD over DC on that side, and then I'm left with AB over AC on that side. Now, I at least then have BD, AB, yes, AC, and DC. I've got all of the components of the answer. I would just now need to rearrange it. So I actually want to have AC as a numerator, don't I? And BD as a denominator. That's kind of all that needs to happen. So you could do it all in one step or in two steps if you wanted. Multiply by AC. I'll just show you in two steps. That would be AC, technically multiplied by BD in the numerator. DC is just AB. And then do you see I could just divide by BD because those two are multiplied, aren't they? Divide by BD. Divide by BD. And then I would get AC over DC equals AB over BD. Now I know theirs is kind of left and right the other way around, but that's the same thing, isn't it? It doesn't really matter if it's on the left hand side or the right hand side. So that's one way of doing it. You can also, if you want, use the sine rule. That is in the mark scheme, so you can see here if you want to go check out the sine rule version. This one to me just made more sense, so that's why I went through this one. Question 23. The diagram shows a sector OACB of a circle with centre O. The point C is the midpoint of the arc AB. The diagram also shows a hollow cone with vertex O. So that's the same O, right? I know it doesn't look like it's to scale, but that's the same O that they're referring to. Over here is now at the top of the cone, and the cone is formed by joining OA and OB. So basically they've taken the radius of the sector and stuck those two lines, those two radiuses together to then create a cone. So A, B, C, and O all represent the same points of the, if you imagine the same piece of paper. Now they've given us some formulas here that they deem irrelevant. The cone has a volume of 56.8 centimeters cubed and a height of 3.6 centimeters. Calculate the size of the angle AOB of sector OACB. So that's what we're looking for eventually, isn't it? I'm probably going to start with the cone. They've given me the formula for the volume of the cone, and they've actually given me the volume of the cone as well as a number. So I'm going to start by setting up that equation. So I've got a third pi. Now I don't know the radius of the cone. It's not the same radius over here, is it? Because have a look at that. OB, which was a radius of the sector, is now the slanted height. If you think of it as like L in this case, the slanted height, isn't it? So I'm just going to leave R as that because I don't know what this is yet. But I do know the height. They've said 3.6, so that's 3.6. And that equals to 56.8. So I can just rearrange this. The only thing I don't know is R. So I can solve it for R. So effectively, I just need to divide by a third pi times 3.6, don't I? So you can divide it in steps, but I just do it all in one. That gives me 15.0666 ... That's obviously the radius squared. So now square root my answer. Keep all the decimals where you can. This is the radius of the cone, 3.88 ... So the radius of the cone, I'm just going to label it so we remember what it is 3.88, roughly. Now, for this one, there's quite a lot of numbers that we're going to be using throughout. So instead of we can't necessarily use the answer button because I might need to come back to this later. You can actually use the storage function if you want. So what you do is you keep your answer here, you go shift, and then wherever yours says STO, click that. Then, do you see how I've got these pink, kind of red or pink letters, A, B, C, D, E, so on? Just choose one of those. Do you see how it said answer has gone to A? So all of the decimals has gone to A. So now I can kind of leave that there and bring it back when I need to. So I've worked out the radius of the cone. It's roughly 3.88. So you can almost tick that off. If you then don't really know what to do, you can also go, well, why have they given me the curved surface area of the cone then? I might as well use that. Even if you don't really know why, I might as well use that, right? So I could work out the curved surface area of the cone because obviously we have pi. We have now got the radius. But L is the slant, isn't it? So I could set up a triangle here. Do you see how I know the height, I know the radius, so I could work out the slant length, or in other words, the radius of the sector. That's the radius of the sector, isn't it? So this is now Pythagoras. Just think of it as a kind of 2D flat triangle. So Pythagoras defined, obviously that's the hypotenuse. So to find, let's just call it OA, squared is 3.6 squared, and then I will use the whole of my decimal, 3.88, from either your answer or your stored function. So if you want to use the stored function, you then press, in my case, it might be the same for yours, alpha, because that's the pink red colour, isn't it? And then I chose A, so then that will copy all of the digits for the 3.88. Now, obviously, I do need to square root this, so I'm going to do my answer square root. So I've got 5.294-ish for the radius of this sector, or the slanted side of the cone. 5.294, obviously dot, 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 dot. Again, if you want to store this one, you can. I'm just going to put store, and then I'll put it into B, just for now, because we might need to use that again. So that's obviously the slanted height, but we know that OA or OB is the same as the radius of my sector, so that's how they're also relating. But I can then use that in this formula, obviously, so come back to what we were actually going to do. The curved surface area of the cone is pi times the radius of the cone, right, which is the 3.88. So you see how I would probably use my storage function there, and then multiplied by my previous answer, which was the 5.294 dot, dot, dot. So in my case, because I've stored them both, I can do pi times A times B. So I'm not losing any of the decimals. I really try not to round anything too soon when I can. So I've got 64.557-ish. Now think how that links also to the sector. The curved surface area of the cone, if you were to kind of open up the cone and lie it flat again, is also the area of the sector. So that's how they also relate. So now if I set up my formula for the area of the sector, this one we should know is obviously the whole circle, pi r squared, times by the angle over 360, which is helpful because I want to find out the angle. So I've got an equation with the angle in it. So now I can just sub some things in. I know the area of the sector is the same as the curved surface area of the cone. So substitute that in, 64.557. Obviously, I'm going to try to use all of the numbers on my calculator, all the decimals. Over here, I do know the radius, but don't get mixed up. It's now the radius of the sector, isn't it? Which is the 5.294 squared. And then obviously then multiplied by the angle over 360, which is the only thing that I don't know, but I also want to know. So now I can just solve this equation. So taking my answer, I'm going to divide by all of pi times by the radius squared. Just remember which one was A and which one was B. B was the 5.294, wasn't it? There, and then I can just times by the 360. You could do that all in one step if you wanted. And there's my angle. So finally, now I can round it. The size of angle A, so 3 significant figures, that would be 264. And there we are. So the diagram shows the positions of 3 towns. Acton A, Barston B, and Chorlton C, ABC. They've then given us this information that they've also obviously drawn on to the diagram. Barston is 8 kilometres from Acton on a bearing of 37 degrees, and Chorlton is 9 kilometres from Barston on a bearing of 150 degrees. Find the bearing of Chorlton from Acton to 1 decimal place. First of all, in terms of bearings, you need to know which angle is this. So it's always written the wrong way round when it says of Chorlton from Acton. So whichever one it's from, that's the north line that you're going to go from in a clockwise direction. So because they've related Acton and Chorlton, I'm going to draw a line between them. If that's not already there, then draw that yourself. Bearings work in a clockwise fashion from the north line. So from Acton, going clockwise from that north line, the angle that they're asking for, the bearing, is from the north line of Acton to the line that connects Acton and Chorlton. Okay, so that's just bearings, that bit there. That's nothing to do with trig. So we want to know that. Now looking at that, do you see how we obviously know the 37 degrees? We're missing this part of the angle, which, now that I've drawn the line AC, happens to be within a triangle. So, having a look at this triangle, with sine and cosine rule, either way you need 4 pieces of information, including the one that you're looking for. So we're looking for the angle, that's 1 piece of information. We've got 2 sides, but nothing else. So I'm missing a 4th piece of information. What could I do? They're not going to give you anything on this question that you don't need. So I've got 37, 150, how can I use those? Well, with bearings, the north lines are obviously all parallel because they're all going in the same direction towards north. So thinking about angles on parallel lines as well, before I even delve into trig, I could work out this angle because of this shape here. That is co-interior angles, they add up to 180. So 180 minus 37, obviously this is a calculator question because you're going to end up with the decimal answer. That gives me 143. As you can see, it's not the same as 150. You don't know if that other side is the same as 150, so don't ever assume anything unless it's explicitly told to you. Then do you see how, because I've got the other two angles, I could work out this angle inside the triangle because all of those angles are around a point and they add up to 360. 360 minus both of those angles will give me another angle inside the triangle, 67 degrees. Now if I come back to my triangle, what do I now have? I have two angles, including the one I want to know, and two sides. It's still a little bit harder because for cosine rule, we could work out the side AC. So you'd get your formula from the formula sheet. As I normally recommend, you can scribble out the letters that they've used for the corners because they don't match what we want. We want to base it with angle A, which is the 67. So if you use a pencil, you can always rewrite the letters. So I want this to be angle A because that's how my formula is based. Therefore, side A is the opposite, which is the one I'm trying to find. This one that used to be A can now be B, so that's side B, and C can stay as it is, side C. So we're trying to find a side, so it's already in the correct format, that's fine. And we just fill in the formula with everything you know, and type it into your calculator. And there is our answer. Now, that is not a side length, remember that is A squared, so you might want to then square root and use your A and S button to copy all of the decimals to get the most accurate answer possible. Now, because this is not our final answer, I'm going to write down a fair few of those decimals for A. So 9.419 ... and this one is in kilometers. Because we've got so much information, we could either use sine rule or cosine rule. I'm going to use sine rule just to kind of demonstrate a different one. With sine rule, you put at the top of the fraction whatever you're looking for. So we're looking for an angle, so all the angles will go at the top. So here we've got sine x, because we don't know what the angle is, over the side 9 kilometers. Obviously, angles always go with sin, cos, or tan, right? So sine of this angle, which is 67, over this side, which I'm going to write down as 9.419, but in my calculator, I'm going to copy the number so I don't miss any digits. Before we put it in the calculator, though, we want to get x as our subject. So first of all, I'm going to multiply across by 9. And if you've seen our previous videos with anything to do with trig, whenever you're looking for an angle, you always have to do the inverse of either sin, cos, or tan. So you see I've got my previous answer still there, so that's fine. I'm going to go straight into sin inverse and type all of this. Normal sin there because we do know that angle is 67. I'm going to put here the answer, so that will copy all of those digits. Times by 9, close the brackets. And you can see you get an answer that does seem like a reasonable angle. If you've got something less than 1, you probably haven't done the inverse correctly. So they've said 1 decimal place, so 61.6. Now, the only thing with that is don't get mixed up and think that that's the final answer. That's just x, isn't it? So in terms of our bearing, step 5, we need to do 37 plus 61.6, which is 98.6 to 1 decimal place. Technically, the bearings have to have the 3 digits, so if it's 98 in that case, we would put 098.6, but I don't think they will mark you down if you forget to do that. So question 24, the diagram shows 8 identical regular octagons joined to enclose a shaded shape. Each octagon has sides of length A. Find, in terms of A, an expression for the area of the shaded shape. Give your answer in the form p brackets 2 plus root 2 a squared. Where p is an integer, you must show all you're working. Okay, so I'm going to split up this shape in the middle because obviously we don't have a formula literally for this kind of star shape. What I can see though is that there's clearly a square there in the middle, and then we've got 4 identical isosceles triangles. So side length A for each side of the octagons, kind of like that, and then the same vertically. So let's first find the area of one of these triangles. I don't have the height of the triangle, so I think I might just use the trigonometric version of the formula. So I would need to know this angle here as well. But I do have regular octagons, so I can use my formula n minus 2 times 180 over n, which will tell me what one of these angles is for the octagons. Now I'll just swap out n to replace it with the number of sides, which is 8. So as you can see, each angle inside the octagon is 135 degrees. And as you can see, I could work out the angle inside the triangle because I've got angles around a point. So 360, subtract both of the 135s, just leaves me with 90. So actually, what we could do with this triangle then is the fact that it's a right-angled triangle means that the A's, here as well, the A is the base and the height, isn't it? actually. So I don't even need to use the trigonometric area now that I know it's 90 degrees. So for the area of a triangle, we've got base times height over 2, so that's a squared over 2, or let's say a half a squared. But there's 4 of them, so then times that by 4. So we'd have 2a squared, the area of all 4 triangles. Now let's have a look at the square. We obviously need to do length times width, which would be the same expression, but we need to figure that out, don't we? Because we know that we've got obviously a here, but we need to now also know the length here. Now that we know that it's a 90-degree triangle as well, we can just use Pythagoras actually. You could obviously, if you wanted to, use cosine rule, things like that. We don't technically need to. We've basically got AA, and we want to know the hypotenuse. That's technically C in terms of Pythagoras' theorem, isn't it? You get a squared plus a squared, so that's 2a squared. So the square root of 2a squared, which would give me just root 2a, because I can square root the a squared. So that's the side there. So if this is root 2a, then the whole length would be 2a plus the other root 2a. And then, because it's a square, to find the area of my square, I can just basically square that, can't I? Times it by itself. Now let's see if I could expand that. That's basically double brackets, isn't it? So 4a squared plus 2 root 2a squared plus another 2 root 2a squared plus the last bit, which would be just 2a squared. So that would simplify to 6a squared plus 4 root 2a squared. Or you could obviously pull out the a squareds and put them together. But for the total area, I just need to add the other 2a squared, because that's my triangles, isn't it? So that's 8a squared plus 4 root 2a squared. Now, I've got the answer, however, I do need to then just rewrite it in their format. So what they've done is obviously factorise out a squared at the end, and also factorise out just a number at the front, haven't they? So you can also see what's in the brackets, just 2 as our first number, and effectively 1 root 2. So they've obviously factorised out 4, and obviously the a squared. So then you're left with just 2 here, and then plus root 2 in the second part. And then we've got what they've got. They said obviously p is an integer, the integer is 4. So I think this one there were a lot of different ways to do it. You could still have used the trigonometric area of a triangle, you could have still used cosine rule if you wanted, especially if you've got a question where it wasn't 90 degrees, or you could just do it more straightforward like this. I think there's loads of different ways to do it. As long as you get to this answer, then I don't think it would really matter. So question 26, we've got here a regular heptagon, so a 7-sided shape. We've been told that the area of triangle ABG at the top is 30 centimeters squared, and to calculate the length of GB. So there's a few things that come to mind here. Obviously, in terms of regular polygons, whatever a shape it is, it's a polygon, we can use the formula to find out one of the angles. That's going to be helpful. N minus 2 times 180. But also I've got a triangle, so I'm thinking anything to do with triangles. Not a right angle triangle, but you might be able to make it into one if you needed to. So we could think basic trigonometry. We could probably think maybe sine rule or cosine rule, that type of thing. Trigonometric area of a triangle. All of that is kind of coming to mind when I take in everything about this question. So they've given us the area of triangle ABG. So we could set up a formula for the area. Now, obviously we do have 2 formulas for areas of triangles. We've got half base times height, which we don't have the base, but we do want to find it. But we also don't technically have the height, so we don't have either of those 2 things. Or we could use our trigonometric area of a triangle, which is half AB sine C. Now, A and B are obviously then the sides of the heptagon, and then the angle between. So we could use either of those. If we did the trigonometric area, we would, as I said, need this angle here. So let's use our angles in regular polygons formula, n minus 2 times 180. That would give you the total in any type of polygon, total degrees, total angles. But I also want to know just one of them, so I divide by how many sides there are. So in this case, I can swap n for 7, because it's a heptagon, it has 7 sides, and work out what one of those angles would be. Now, unfortunately, it is a really long number, so I might just save this in my storage option. So Shift STO, I'm going to choose A. I'm just going to keep that there. But it's about 128.57, and that's obviously degrees. So each of those angles, each of them is 128.57. So I've got that. You could label one of the sides as x if you wanted, but because it's regular, they're both x. So I'm going to set up my equation with that. Half AB, so that would be x times x, which is x squared. Sine of the angle would be sine of 128.57, ... And I know that that equals 30. So do you see how I could rearrange this to work out one of the sides of the actual heptagon? So I've got my answer here anyway, so for now I can use that. But I would probably do 30 divided by the half and the sine. So divided by 1/2 times sine of my answer. So x squared is 76.74, so now I'll just square root that answer. So x, each side length, would be about 8.76. Again, I might save that for later just in case. I'm going to put it into B, 8.76. So now, I'm just going to change that one so that you can see. I know that this side, or technically all of the sides, but even if you just look at the triangle, the side AB or AG, both of them are about 8.76 centimetres. So I've got the angle, 128, I've got the two sides, and I just want to find out GB. So now that to me is screaming cosine rule because I've got 3 sides and 1 angle. Obviously I'm trying to find one of the sides, but that's fine. 3 sides, 1 angle. So cosine rule, we want to find a side, so that's the GB in this case, isn't it? GB squared, again this is on your formula sheet, is B squared plus C squared, so those are the two sides around the angle, aren't they? So that's technically 8.6 squared plus the other 8.6 squared, minus 2 times 8.6 twice. So you could write that squared if you wanted to. And then obviously cosine this time of the angle 128. So I can type all that in. So as I said, I saved 8.6 ... to B, so that's what I'm going to use. You could obviously use your answer button if it was still the previous answer. Just make sure that it obviously is. And then I'm going to use A because that was, if you remember, I did actually save that for my angle to get all of those decimals. Now this is obviously GB squared as we said, so square root that. So I've got GB is 15.78 ... but let's have a look. 3 significant figures, so 15.8. So GB is 15.8, obviously to 3 significant figures. So those are some of the hardest Edexcel past paper, obviously calculator questions. If you haven't already checked out the most repeated Edexcel calculator questions, that would be the next one to have a look at so you can see kind of what is the most likely to maybe come up in paper 2 or paper 3. But otherwise, thanks for watching this video. If you found it helpful, make sure to like and subscribe and leave down below any questions or comments that you might have.